Greetings, this is Chemistry with Nav. In this video today, we're going to take a look at periodicity and the melting points of the period 3 elements. You might be asked to describe and explain the trend in the melting point of the period 3 elements, and the basic line for that would be that it increases from sodium up to silicon and it decreases thereafter down to argon. But that's a description, it doesn't explain why we get that trend at all. In order to explain it, we need to look at things in different sections, and we're looking at the type of bonding and structure that's present. So if there's anything here that you're unfamiliar with, then you probably need to go back and look at bonding and structure in general. We start off with sodium to aluminium, and here we have metallic bonding. And in metallic bonding, you have a strong electrostatic attraction between the positive metal ions and the delocalized electrons. But as you go from sodium to magnesium to aluminium, you end up making Na+, Mg2+, and Al3+. So you are getting ions with a greater charge, which means that there's also more delocalized electrons. So there's a greater attraction, so that the melting point increases. And next is silicon. And in silicon, you have giant covalent bonding. And the giant structure, the giant lattice in silicon, means that every silicon atom is bonded to 4 other silicon atoms. So when you try to melt it, you have to break all 4 of those bonds per atom, which means that it requires a huge amount of energy. And that's why you've got the very large peak going up to silicon there about 1700 Kelvin. After silicon, though, you have these 4, and there are simple covalent structures in place, which basically means that there are molecules, and if you have molecules, then you must have intermolecular forces. And because we have an element here, or all 4 of these are elements, there's going to be no hydrogen bonding, and there will be no permanent dipoles. So the only thing that we're relying on is the London dispersion forces, or the van der Waals forces. These forces are instantaneous dipole-induced dipole interactions. And what that means is that there is a dipole there, but it's just there because of an imbalance of electron density. So what's important here is the size of the molecule, because the London forces are greater as you have a greater electron count. And what we get with these structures is P5, S8, Cl2, and then argon there is monoatomic. So with the slight increase from P5 to S8 in terms of mass of the molecule, then you have an increase in the melting point. But then Cl2 is far smaller, far lighter, therefore the melting point goes down, and argon monoatomic, it goes down again. So with those last 4, we're just looking at intermolecular forces.